Number 9, in 2000, the average sales price of a car was $22,000. So 2000 is our beginning time. So for A naught, which is this right here, we're going to put in $22,000 because that was our initial price for a car in 2009. Okay, it says by 2009, that's 9 years later, so I'm going to plug in 9 for my time. It had increased to 28,000, so my new amount is 28,000. Use the exponential growth model to find the exponential growth function that models the data. So my answer is going to be an equation, not a number, and we need to round k to 3 decimal places. So I'll divide both sides by 22,000. See, that's going to be 14 over 11. Then to get rid of the e, we take the natural log of both sides, and the natural log cancels out the e. So it just leaves us k times 9. So then we divide both sides by 9. So I'm going to have the natural log of 14, actually, hold on, over 11. And I divide that answer by 9. So I get 0.027, since I'm rounding to 3 decimal places for k. So k is 0.027. So my final answer needs to be A equals 22,000 e to the 0.027t. You want to have A0 or A naught and k plugged in, and this will be your final answer. Number 10, the population growth of China can be modeled by this equation, where A is the population in millions and T is the number of years after 1984. What was the population of China in 1984? Well, that's our initial time, so it's just the number right in front of here, 987 million. At what rate is China's population increasing each year? The rate is the K. 0.034 translates to 3.4%. What was the population of China in 2004 to the nearest person? So since it was 1984, 2004 is 20 years later, so I plug in 987 times e to the 0.034 times 20. We get 1,948, or well, yeah, we'll just do that. So 1948 million, so 1948 million, which is really like 1.9 billion. In what year will the population of China be 1,738 million? So we plug 1738 in for A, and we solve for T. So I divide both sides by 987. I get 1.760. Or 1.761. And then to get rid of the e, we take the natural log of both sides. Remember, the natural log cancels out the e. So we get natural log of 1.761 equals 0.34, or excuse me, 0.034. 0.034 t. So now I just divide both sides by 0.034. So natural log of 1.760 and so on, divided by 0.034, giving us 16.64. So that's 16 years after 1984, so it would be the year 2000. So again, our answer was 16 years and some change. So that's 16 years later from 1984, making it the year 2000. Okay, number 11, the table shows the walking speed of an average citizen in a city whose population is, sorry, there's a typo there, whose population X is in thousands. Plug these values in your calculator and run an exponential regression. So remember to plug them in. Whoop. Sorry about that. Okay, to plug them in, we go to Stat, Edit, and we need to plug in 5.5, 14, 71, 138, and 342. I'll delete that value because I don't need it. And then I need 3.3, 3.7, 4.3, 4.4, 4.8. And it wants me to run an exponential regression. So I go to Stat, Calc, I go down to the one that's exponential. I think it's 0 maybe. Yeah. And I don't know if we'll need it or not, but we'll plug this in for y1 and get our answer. Okay, so it says what is the equation that your calculator finds? And then part B is what is the r squared value? Okay, the equation is 3.663 times 1 raised to the x. So 3.663 times 1 raised to the x. And this is, let me just do it that way. That's better than times. So that's the equation it finds. And the r squared value is 0.708, which is really not very good. We want something closer to 1. 0.708. Okay, this next slide is the same problem. Plug these values in your calculator and run a logarithmic regression. What is the equation your calculator finds? So let's try the logarithmic regression. So I go back to Stat, Calc, 9 is the logarithmic one, and I'm going to plug this in y1, hoping this one's going to be better than the exponential one. And I get 2.735 plus, and that's 0.352 times the natural log. And my r squared is 0.992, which is much, much better. So based on the graphs and the r squared, it's clear that the natural log or the logarithmic is our better choice. Okay, write the equation in its equivalent form. Remember, it's log BAPS. This is our base, our answer, and our power, meaning the exponential form should be base raised to my power equals my answer. 13. Remember, we want log BAP. This is the base, this is the power, that's our answer. So we do log base 5 of 125 equals 3, because it's log BAP, base, answer, power. Okay, 14 you can just plug in your calculator. You should get 0. 15 you should plug in your calculator. You should get 2. This one, the 4 and the 4 cancel out, so it just leaves you with 5x minus 1. Same idea here, the e and the natural log cancel out, just leaving you 45. 18, we want to find the domain. Logs have to be positive, so x plus 1 has to be greater than 0. So now I just subtract 1 from both sides, and I get x is greater than negative 1. And that would be my domain. Okay, 19 has x minus 6 squared. Now since it's squared, it's always going to be positive, or I should say non-negative. So the only thing you have to worry about is 0. X minus 6 squared cannot equal 0, because logs can't be negative and they can't be 0. Well, we know it won't be negative because it's squared, but it still could be 0. So when it's squared, we set it not equal to 0. Take the square root of both sides, and we get x cannot equal 6. So x can be anything except 6. And we'll finish this on one more video.